Welcome to the deep dive, where we take complex information and distill it into clear, surprising insights for you. For decades, the promise of robots in our daily lives felt like a distant science fiction dream. They could assemble cars, yes, or perform highly repetitive tasks, but ask one to adapt to a messy home environment or understand a nuanced instruction.
hmm
That was the truly hard problem. Today, we're diving into a fascinating technical report from ByteDance that suggests that era of specialized, often clunky robots might be ending.
Right.
We're looking at GR-3, a robot that's less industrial worker and far more akin to a truly capable assistant.
And this deep dive focuses on their GR-3 technical report, which came out July 23, 2025. Our mission really is to understand GR-3's capabilities, which are pretty remarkable, the innovative ways it learns and maybe what its development means for the future of robots moving out of factories and, into our everyday spaces.
Let's unpack this. When you say generalist robot, for someone who has followed robotics for a while, that sounds like, well, the holy grail. Why is that capability specifically such a monumental leap compared to what robots could do even just a few years ago?
Well, traditionally, training a robot for a new task meant extensive, really costly retraining. It often took weeks, maybe even months of specialized programming.
Right, very specific skill.
Very specific. Each new object, each slightly different environment, meant engineers had to basically go back to the drawing board.
hmm
GR3, it fundamentally shifts this paradigm. It's described as a large-scale vision-language action model, a VLA model.
VLA.
So this means it processes visual information, it understands language, and then translates that into physical actions. And crucially, not just for one specific task, but for a broad range of activities it hasn't explicitly encountered before. It's a really critical step towards robots that aren't just programmed for one thing, but can genuinely adapt and generalize.
So the report highlights GR3's exceptional capabilities right from the start. It says it can generalize to novel objects it has never encountered, adapt to entirely new environments, and even understand and follow instructions that involve abstract concepts.
Uh-huh.
Beyond that, it's designed for efficient fine-tuning using minimal human data that allows for rapid, cost-effective adaptation to new situations. That ability to quickly adapt with just a little data seems like a critical bottleneck they've overcome for real-world deployment.
It absolutely is. And furthermore, GR3 demonstrates robust and reliable performance in complex long-horizon tasks.
So multi-step operation?
Yeah, multi-step operations unfolding over time, and also dexterous tasks, which involve really intricate manipulation. This includes scenarios needing both hands, bimanual manipulation, and mobile movement, where the robot actually needs to navigate its environment.
Okay.
Its ultimate goal, as stated, is to assist humans in daily life, which suggests a move beyond purely industrial settings into more personal assistance-type roles.
That's incredible. The capabilities are really quite something. But the real question, the one everyone wants to know, is how? What's the secret sauce behind getting a robot to be this adaptable and intelligent? I understand it starts with a truly unique training recipe.
Right. The core of GR3's learning comes from 3 distinct data sources, and each contributes uniquely to its intelligence. First, there's co-training with web-scale vision language data.
Web scale. So huge amounts of data.
Massive. It's curated from diverse sources covering tasks like image captioning, where the robot learns to describe images, visual question answering, where it answers questions about images, and image grounding, linking words to specific objects in an image.
Okay.
This vast exposure allows GR3 to understand novel semantics and generalize to entirely unseen objects in a zero-shot manner.
Zero shot meaning without prior specific examples.
Correct. This is a monumental step because it means the robot doesn't just recognize a specific chair it's seen before. It understands the concept of chair and can interact with any chair, even one it's never encountered. And critically, it helps the robot understand abstract concepts, sizes, spatial relationships, common sense knowledge, things vital for nuanced real-world interaction.
So if it's understanding abstract concepts and common sense knowledge, are we talking about something like an AI's intuition here, or is it still fundamentally different from how humans think? It sounds like it's inferring information, much like we do.
It represents a significant move towards broader, more intuitive understanding, certainly moving beyond mere pattern recognition. The robot learns to build a more generalized model of the world, not just memorize specific instances it saw in training. Now, the second source is efficient fine-tuning with human trajectory data.
Human trajectories. How do they capture that?
This data is collected using VR devices like the PKI-4 Ultra Enterprise. And this method is remarkably efficient. They report collecting human trajectories at about 450 per hour,
Wow, 450 an hour.
which substantially outpaces the, say, 250 trajectories per hour you might get from teleoperating a robot directly.
Okay.
This speed difference allows for rapid and, importantly, cost-effective adaptation to new settings with very little data. Sometimes, maybe as few as 10 human trajectories per object are enough to teach the robot a new task for that specific object.
That efficiency sounds almost too good to be true. What does that mean for the practical deployment of these robots if you can teach them new tasks that quickly?
Well, it could fundamentally democratize robot deployment. Historically, introducing a new item or even a slight variation in a task meant, extensive, costly retraining by expert engineers.
Weeks, months, right.
Exactly. GR-3's ability to adapt with just 10 human demonstrations means maybe a small business, or potentially even an individual, could teach a robot a new task in an afternoon, rather than needing a whole team of specialists for months. It drastically lowers the barrier to entry for custom robotic solutions.
That's a powerful shift. Now, the third data source is effective imitation learning with robot trajectory data. This data is collected through real-world teleoperation, but with a specific innovation, a data collection scheduler. Can you walk us through how that scheduler makes a difference?
Sure. This scheduler basically ensures diversity in the collected data. It informs the human teleoperators about the specific actions, object combinations, and even background settings to focus on.
So it's guiding the data collection.
Precisely. Instead of just random data collection, it's a targeted approach. It makes sure the robot gets a broad and varied learning experience, which is critical for generalization. Now, beyond these diverse data sources, the report also details some key architectural design choices contributing to GR-3's capabilities. One is the application of RMS norm within its action diffusion transformer blocks.
RMS norm sounds very technical. For those of us not deep into neural network architectures, can you paint a picture of what training stability means here? Is it like making sure the robot doesn't, I don't know, forget half of what it just learned or get stuck in the loop?
That's a good analogy. Think of it like trying to teach a complex skill. If the learning environment is unstable, you might learn something one day and completely forget it the next, or develop strange, ineffective habits. RMS norm helps keep GR-3's learning process focused and consistent during its massive training.
Okay.
It ensures it builds knowledge reliably without erratic behavior or something called catastrophic forgetting, which is a huge hurdle in complex AI models. So this modification significantly improves that training stability and, importantly, enhances the robot's language following capabilities.
And the other significant innovation mentioned is incorporating a task status, which could be ongoing, terminated, or invalid as an additional action dimension during training. How does that help?
Well, this auxiliary supervision is a powerful mechanism. It forces GR-3 to pay closer attention to the language instruction because it's not just predicting what action to take, but also the status of the task itself based on the instruction.
Ah, I see.
It even trains the robot to predict an invalid status if a command, say, put the knife into the woven basket when there are no knives around, just cannot be completed given what it sees.
So it knows when it can't do something.
Right. And this capability boosts its instruction-following skills, preventing the robot from attempting impossible or nonsensical tasks. That's critical for safety and efficiency, especially in unpredictable environments.
Okay, so all this intelligence, this learning, it needs a physical form to operate in the real world, and that's where the ByteMini robot comes in.
That's right. ByteMini is described as a versatile 22 degrees of freedom bimanual mobile robot.
22 degrees of freedom, wow.
Yeah, it's specifically designed for flexible manipulation. It features a 7-F, 7 degrees of freedom, unbiased robotic arm. What's special about this arm is its unique sphere wrist joint.
A sphere wrist joint.
Yes, which provides more human-like dexterity and allows the robot to operate effectively even in confined spaces, overcoming limitations you might see in more traditional arm designs.
A sphere wrist joint. That sounds really innovative. How does that translate into actual practical advantages for the robot? What can it do that a more traditional arm might struggle with?
That joint is quite crucial. Traditional robot arms often have limited reach, or they can get tangled trying to operate in tight spaces, or even just manipulate objects close to their own body.
Right. Workspace limitations.
The sphere wrist, much like a human's, allows for incredible flexibility and sort of elbow room even in confined areas. The design allows the arms to perform delicate operations right within the robot's own chest area, which is remarkable for potentially complex self-maintenance or intricate assembly tasks close in. It's about achieving more human-level dexterity in places you might not expect.
Reliability is also mentioned as a key design element, both for collecting all that data and for actual task execution. It sounds like they built this robot to be a real workhorse.
It seems designed for robust operation, yes. It uses an omni-mobile platform so it can move in any direction integrated with a lift mechanism. This gives it stable movement and height adjustment so it can reach objects on different surfaces, from the floor up to countertops.
Adaptable height, okay.
And to further enhance reliability and ensure smooth, consistent motion, the actuators in the arms are designed based on the quasi-direct drive principle. This is known for stability and high transparency.
Quasi-direct drive, that sounds like it's about giving the robot a better feel for what it's touching or moving. Is that the idea?
That's essentially it. Think about your own arm. You can feel resistance, weight, subtle forces. Traditional robots often have gearboxes that introduce friction or slop, making them less responsive and harder to control precisely. Quasi-direct drive minimizes that, giving ByteMini potentially very fine control and responsiveness, almost like the robot can feel the cloth or the object it's manipulating. That's crucial for those delicate tasks.
Makes sense.
Plus, they mentioned user-friendliness. A portable screen, a long-lasting battery delivering over 10 hours of endurance apparently, and a wireless e-stop for safety.
Always important.
And it integrates RGBD cameras, depth sensing cameras on its head and wrists. This allows for close-up observation during fine manipulation, providing the detailed visual feedback needed for precision work.
Okay, so the report then moves into the moment of truth, rigorously evaluating GR-3's performance. They put it through 3 challenging real-world tasks, and importantly, they consistently compare it to the state-of-the-art baseline method called Zero. This comparison really helps illustrate the scale of GR-3's advancements.
Right. In the first one, generalizable pick and place, GR-3 shows superior generalization, tackling some really tough challenges. For unseen instructions involving abstract concepts, the example given is put the animal with tentacles into the carton, a command it had never heard before.
Right, it needs to understand tentacles.
GR-3 significantly boosted the success rate. Zero got 40%, but GR-3 achieved 77.1%.
That's a big jump.
And for unseen objects from novel categories it had never encountered, GR-3 achieved a 57.8% success rate, compared to Zero's 40%. The co-training with that web-scale vision language data was clearly crucial for these zero-shot capabilities.
And the fine-tuning.
What's particularly striking is that with just 10 human trajectories per object, GR-3's success rate on those unseen objects jumped further, from 57.8% up to 86.7%. That showcases really remarkable few-shot learning.
That is a significant leap with minimal new data. For a robot to adapt that quickly with such little human input truly sets it apart.
Then for long-horizon table bussing, this is a task requiring the mobile base to move across a larger workspace and perform multiple steps, like packing food, putting utensils in a box, throwing trash in a bin.
A more complex sequential task.
GR-3 again outperformed Zero, particularly in the instruction-following setting. This task combines perception, mobile navigation, and sequential manipulation. GR-3 achieved a 97.5% success rate versus Zero's 53.8%.
Almost perfect versus just over half.
And when GR-3 achieves 97.5% success here, that's not just a number. It addresses one of the really persistent failures in robotics: sequence prediction and task completion over longer periods. Historically, robots might complete step 1 perfectly, then fail catastrophically on step 2 or 3 because they couldn't plan ahead or recover from small deviations.
Right, things go off script.
GR-3 apparently followed complex instructions strictly, even for novel destinations that didn't appear with objects during training. And it could also accurately determine and refrain from executing those invalid tasks we discussed earlier, which is vital for real-world robustness.
And finally, the ultimate test of fine motor skills: dexterous cloth manipulation. This is notoriously difficult for robots because fabric is deformable, unpredictable.
Exactly. And here, GR-3 excelled at tasks like hanging clothes onto a drying rack. It achieved high average task progress, even when the clothes are rotated or crumpled, or even with entirely unseen instances, like short-sleeved shirts, which weren't in the training data at all.
So it adapted to different clothing types?
It seems so. The report specifically noted that the most challenging part, pulling out and placing the left shoulder correctly on the hanger, was navigated robustly by GR-3. This demonstrates a level of adaptability and fine motor control that's quite advanced, moving beyond just rigid object manipulation into the tricky realm of soft, unpredictable materials.
That's impressive. Folding clothes is still hard for me.
Well, while GR-3's performance here is impressive, the report does imply that the next big hurdle in cloth manipulation will likely involve even more nuanced tasks like folding clothes precisely, or perhaps ironing, which require an even deeper understanding of material properties and finer motor control. Still, hanging is a big step.
So summing up then, what does this all mean for us? GR3 demonstrates superior generalization, really efficient adaptation through human demonstration, and remarkable robustness across complex, real-world manipulation tasks. It feels like a testament to how intelligent design and diverse data can push robotic capabilities forward into genuinely new frontiers.
I agree. This report on GR3 truly showcases compelling progress towards creating intelligent generalist robots. Its innovative approach combining diverse data types, from web-scale vision language data to efficient human trajectory data, and targeted robot demonstrations allows it to handle complex instructions and generalize to novel scenarios with notable reliability.
Now, the report does acknowledge ongoing challenges. Things like handling grasping objects with truly unseen shapes or recovering from states that are way outside its training distribution during actual operation.
Sure, the real world is messy.
But the capabilities demonstrated by GR3 and the ByteMini robot seem to bring us significantly closer to a future where generalist robots can genuinely assist us in our daily lives.
And this raises an important question, maybe for you listening. How might these advancements in robot learning, this blend of diverse data types and human teaching methods, reshape our approach to training complex AI systems even beyond just robotics? Think about how these integrated learning methods could apply to other forms of AI that need to understand and interact with the world, pushing the boundaries of what general intelligence might actually mean for machines.